What is the smallest thing in our universe? The smallest thing in existence is so tiny, almost impossible to imagine. At the human scale of 1 meter, the scale our senses understand without tools, the scale of height, distance, and movement through a room. And at this level, matter appears continuous, solid, and stable. Nothing at this scale reveals the layered structure beneath it. A table feels smooth, skin feels unbroken, air feels empty, and space appears uniform. However, physics shows that this apparent continuity is not fundamental. What appears solid at 1 meter is built from structures many orders of magnitude smaller, and the search for the smallest thing in the universe begins by moving down through these layers using experiment, not imagination. At around 10 micrometers, which is 10 to the minus 5 meters, we reach the scale of human skin cells. A skin cell is roughly this size, and it cannot be resolved by the naked eye because visible light has wavelengths on the order of hundreds of nanometers, which are too large to distinguish structures this small. Microscopes revealed that skin is not a smooth sheet, but a collection of individual cells packed together. Each cell is bounded by a membrane composed of lipid molecules arranged in a bilayer. Inside the cell is cytoplasm, a fluid filled with proteins, ions, and organelles. The nucleus of the cell contains genetic material organized into long strands of DNA. At this level, matter is not continuous. It is organized into biological units, and each unit is made from molecules. DNA has a width of about 2 nanometers, or 2 times 10 to the minus 9 meters. Its structure was determined through X-ray diffraction experiments in the 20th century, where X-rays scattered off atoms in crystalline samples produced patterns that could be analyzed mathematically to determine molecular geometry. DNA is a double helix formed by 2 strands of nucleotides linked by hydrogen bonds. The backbone consists of sugar and phosphate groups, while nitrogen bases form the internal rungs of the ladder structure. At this scale, matter is no longer biological tissue, but molecular structure, and molecules are themselves built from atoms. An atom has a typical diameter of about 1 angstrom, which is 10 to the minus 10 meters. The structure of the atom was established through a sequence of experiments. In 1897, J.J. Thomson identified the electron using cathode ray tubes and demonstrated that atoms contain negatively charged particles smaller than hydrogen. In 1909, Ernest Rutherford conducted the gold foil experiment, in which alpha particles were fired at thin metal foil. Most particles passed through with little deflection, but a small fraction scattered at large angles. This showed that the atom contains a dense, positively charged nucleus, occupying a tiny fraction of the atomic volume. The atom is therefore mostly empty space, with electrons existing in quantum states around the nucleus. Quantum mechanics later described these electrons not as particles in fixed orbits, but as probability distributions governed by wave functions. The atomic nucleus has a diameter on the order of 1 femtometer, or 10 to the minus 15 meters. It consists of protons and neutrons bound by the strong nuclear force. The neutron was discovered in 1932 by James Chadwick through experiments involving beryllium radiation that could not be explained by known charged particles. The strong force acts at very short distances and overcomes the electromagnetic repulsion between positively charged protons. Nuclear binding energy arises from this interaction and explains why nuclei remain stable despite internal electric repulsion. At this level, the structure of matter is governed by quantum chromodynamics, the theory describing the strong interaction. We've split the atom, we've split the nucleus, we've split the proton. So what's left? What is the smallest thing that physically exists? Protons and neutrons are not elementary. In the 1960s, Murray Gell-Mann and George Zweig proposed that hadrons are composed of smaller constituents called quarks. This idea was confirmed experimentally in deep inelastic scattering experiments, performed in 1968 at SLAC National Accelerator Laboratory. High-energy electrons were directed at protons, and the scattering patterns indicated the presence of point-like internal components. A proton is composed of 2 up quarks and 1 down quark, bound together by gluons, which mediate the strong force. Quarks carry fractional electric charges and interact through color charge. The theory describing their behavior is quantum chromodynamics, which predicts confinement, meaning quarks cannot be isolated individually under normal conditions. Experiments at increasingly high energies have probed quarks and electrons down to distances of about 10 to the minus 19 meters. Within this resolution, both quarks and electrons behave as point-like particles with no detectable size or substructure. These measurements come from high-energy particle collisions in accelerators, where scattering angles and energy distributions are analyzed to infer internal structure. So far, no deviation from point-like behavior has been observed. This defines the smallest measurable structure currently confirmed by experiment. If quarks or electrons have internal components, those components must exist at scales smaller than 10 to the minus 19 meters. Electrons are classified as elementary leptons in the standard model of particle physics. They do not participate in the strong interaction and show no evidence of compositeness. Precision measurements of the electron's magnetic moment match theoretical predictions from quantum electrodynamics to extraordinary accuracy. This agreement supports the view that the electron is not composed of smaller constituents within current experimental limits. The standard model describes 12 fundamental fermions, including 6 quarks and 6 leptons, along with gauge bosons that mediate forces. These particles are not described as tiny solid objects, but as excitations of quantum fields that exist throughout space. In this framework, each type of particle corresponds to a field, and a particle is a quantized excitation of that field. The Higgs field, confirmed experimentally in 2012 at CERN, using the Large Hadron Collider, gives mass to certain particles through its interaction mechanism. The field concept changes the question of smallness because it suggests that what we detect as particles are localized disturbances rather than fundamental solid units. This raises a distinction between the smallest measurable particle and the smallest meaningful length scale. The smallest measurable structure is defined by the highest energy experiments performed so far, which probe distances around 10 to the minus 19 meters. However, theoretical physics predicts a more fundamental scale known as the Planck length. This length is derived from 3 constants: the speed of light, the gravitational constant, and the reduced Planck constant. Introduced through dimensional analysis by Max Planck, the Planck length is approximately 1.6 times 10 to the minus 35 meters. At this scale, quantum effects of gravity are expected to become significant, and spacetime itself may no longer behave as a smooth continuum. Unlike the electron or quark scale, the Planck length has not been measured directly. No experiment has probed distances anywhere near 10 to the minus 35 meters because doing so would require energies far beyond current technological capability. At such scales, combining quantum mechanics and general relativity becomes necessary, and a complete theory of quantum gravity is still under development. Some theoretical approaches suggest that spacetime may be quantized, meaning there could be a smallest possible unit of length below which the concept of distance loses physical meaning. Other approaches, such as string theory, propose that fundamental entities are one-dimensional strings with characteristic lengths near the Planck scale. However, these ideas remain unconfirmed by experiment. The central scientific tension therefore rests on 3 candidates. The first candidate is the elementary particle, such as the quark or electron, which appears point-like down to current experimental limits. The second candidate is the quantum field, which underlies all particles and may represent a more fundamental description of reality. The third candidate is the Planck length, which may define the smallest meaningful unit of spacetime itself. The smallest measurable structure is determined by experiment and currently lies at about 10 to the minus 19 meters. The smallest theoretical structure arises from fundamental constants and lies at about 10 to the minus 35 meters. Between these 2 scales lies a vast gap of 16 orders of magnitude. This gap represents territory that has not been explored directly. Future experiments may extend the measurable limit by increasing collision energies and improving detector precision. But reaching the Planck scale remains far beyond foreseeable technology. As of now, physics provides a clear boundary. Quarks and electrons are the smallest confirmed point-like entities, and the Planck length is the smallest theoretically significant scale predicted by our current understanding of nature. The question of the smallest thing in the universe, therefore, has two precise answers. Experimentally, the smallest measurable structures are elementary particles with no observed size down to 10 to the minus 19 meters. Theoretically, the smallest meaningful length scale is the Planck length at 10 to the minus 35 meters, where new physics is expected to emerge. Whether either of these represents an absolute limit remains an open scientific problem grounded in measurable evidence and mathematical theory. The first breakthrough: atoms are not indivisible. At the beginning of the 19th century, the atom was considered the smallest possible unit of matter, not because anyone had seen it directly, but because chemical reactions seemed to follow strict patterns that suggested matter was built from tiny, indivisible pieces. The first major scientific framework for this idea was developed by John Dalton in the early 1800s. Dalton was not working with microscopes powerful enough to see atoms, and he was not studying electricity or subatomic particles. He was studying gases and chemical reactions, and what he noticed was consistency. When elements combined to form compounds, they did so in fixed ratios by mass. Water always formed from hydrogen and oxygen in the same proportion. Carbon dioxide always contained the same mass ratio of carbon to oxygen. These patterns were too precise to be random. Dalton proposed that matter was made of tiny particles called atoms, that atoms of a given element were identical to each other, and that chemical reactions were rearrangements of these atoms rather than transformations of matter into something else. Dalton's atomic theory explained a wide range of chemical observations. It accounted for the law of definite proportions and the law of multiple proportions. It provided a simple and powerful picture of matter. Atoms were treated as solid, indivisible spheres, each element defined by a specific type of atom with a unique mass. For several decades, this model worked extremely well. It predicted how substances would combine and how much of each element would be required in a reaction. There was no experimental reason at that time to question whether atoms themselves might contain smaller parts. They were considered fundamental, the final building blocks of matter. The first serious challenge to this idea came from experiments involving electricity in gases. In the late 19th century, scientists were investigating how electric current travels through evacuated glass tubes. These tubes contained very low pressure gas and metal electrodes at each end. When a high voltage was applied, a glowing stream appeared inside the tube. These streams were called cathode rays because they seemed to originate from the negative electrode, or cathode. The nature of cathode rays was unclear. Some scientists believed they were waves traveling through the ether, while others suspected they were particles. In 1897, J.J. Thomson performed a series of careful experiments that changed the understanding of matter. Thomson used a cathode ray tube fitted with electric and magnetic fields that could deflect the beam. If cathode rays were waves, their behavior under these fields would follow certain patterns. If they were charged particles, they would bend in predictable ways according to the strength of the fields and their charge-to-mass ratio. Thomson observed that the cathode rays were deflected by both electric and magnetic fields, and the direction of deflection showed that they carried a negative electric charge. By measuring the amount of deflection and knowing the strength of the applied fields, Thomson calculated the charge-to-mass ratio of the particles in the beam. He found that this ratio was much larger than that of any known ion, which implied that either the charge was enormous or the mass was extremely small. Further analysis showed that the mass had to be tiny compared to that of a hydrogen atom. The particle discovered in these experiments became known as the electron. Its mass was later measured to be approximately 9.11 times 10 to the minus 31 kilograms. This value is roughly 1/1800th of the mass of a proton. The existence of a particle smaller than the atom meant that atoms could not be indivisible solid spheres. They had internal components. Thomson proposed a new model of the atom to account for this discovery. In his model, sometimes called the plum pudding model, the atom consisted of a diffuse positive charge spread throughout a spherical volume, with negatively charged electrons embedded within it. The positive charge balanced the negative charge of the electrons, making the atom electrically neutral overall. This model explained how electrons could exist inside atoms without the atom having a net charge. However, it did not yet provide a clear picture of how charge and mass were distributed within the atom. The next breakthrough came in 1909 with an experiment conducted under the supervision of Ernest Rutherford. Rutherford and his colleagues directed a beam of alpha particles, which are positively charged helium nuclei, at a very thin sheet of gold foil. The thickness of the foil was only a few hundred atoms. According to the prevailing plum pudding model, the positive charge inside the atom was spread out evenly. Therefore, the alpha particles, which were much heavier than electrons, should have passed through the foil with only slight deflection, since there would be no concentrated region of positive charge strong enough to repel them significantly. Most of the alpha particles did pass straight through the foil, which confirmed that atoms are mostly empty space. However, a small fraction of the particles were deflected at large angles, and some even bounced almost directly backward. This result was completely unexpected. Rutherford later remarked that it was as surprising as if a shell fired at tissue paper had bounced back. The only way to explain such large deflections was to assume that nearly all the positive charge and most of the mass of the atom were concentrated in a tiny central region. This central region became known as the nucleus. From the scattering data, Rutherford was able to estimate the size of the nucleus. It was found to be on the order of 10 to the minus 15 meters, which is about 100,000 times smaller than the diameter of the atom itself. This meant that the atom is mostly empty space, with electrons occupying the outer region and a dense nucleus at the center. The plum pudding model could not account for these observations and was replaced by the nuclear model of the atom. The discovery of the nucleus introduced a new problem. According to classical physics, electrons orbiting a nucleus should continuously emit electromagnetic radiation because they are accelerating charges. As they lose energy, they should spiral inward and collapse into the nucleus within a fraction of a second. Yet atoms are stable. Matter does not collapse. This contradiction required a new theoretical framework. In 1913, Niels Bohr proposed a solution that combined Rutherford's nuclear model with ideas from early quantum theory. Bohr suggested that electrons can occupy only certain allowed energy levels, or quantized orbits, around the nucleus. In these specific orbits, electrons do not radiate energy despite being in motion. Radiation occurs only when an electron transitions from one allowed energy level to another, emitting or absorbing a photon with energy equal to the difference between the levels. Bohr's model successfully explained the spectral lines of hydrogen. When hydrogen gas is excited, it emits light at specific wavelengths rather than a continuous spectrum. These discrete lines correspond to electrons dropping from higher energy levels to lower ones. Bohr's equations predicted the exact wavelengths of these lines with remarkable accuracy. This provided strong evidence that atomic structure is governed by quantization at a fundamental level. Although Bohr's model was later refined by the development of full quantum mechanics, it established an essential principle. The atom is not a solid sphere. It is a structured system consisting of a small, dense nucleus surrounded by electrons that occupy discrete energy states. The mass of the atom is concentrated in the nucleus, while the size of the atom is determined by the distribution of electron probability around that nucleus. The combined results of Thomson's cathode ray experiments, Rutherford's gold foil scattering, and Bohr's quantized orbits permanently changed the understanding of matter. The atom was no longer the smallest indivisible unit. It was a composite structure. It contained negatively charged electrons and a positively charged nucleus. Later discoveries would reveal that the nucleus itself contains protons and neutrons, and that protons and neutrons are made of quarks. But the first major step was recognizing that atoms have internal parts. The cathode ray experiment demonstrated that atoms contain electrons, particles with a well-defined negative charge and a tiny mass of approximately 9.11 times 10 to the minus 31 kilograms. The gold foil experiment demonstrated that the atom's positive charge and most of its mass are concentrated in a nucleus, occupying a minute fraction of the atomic volume. The scattering results showed that most alpha particles passed through the foil with little interaction, confirming that atoms are mostly empty space, while a small number were deflected sharply, revealing the presence of a dense central core. This shows atoms are not the smallest building blocks of matter. They are structures. They have internal components with measurable properties. The idea of indivisible atoms was replaced by a layered model in which matter has deeper levels of organization. This realization marked the beginning of modern atomic and particle physics, and it opened the path to the later discoveries of nuclear structure and subatomic particles. The atom, once considered fundamental, became a system composed of smaller entities governed by both electromagnetic and quantum laws. The indivisible sphere was replaced by a structured, mostly empty, quantum mechanical system, and the search for the smallest thing in the universe moved to a deeper level. Inside the nucleus, protons and neutrons. At the start of the 20th century, the atom had already been broken open once. The work of Ernest Rutherford had shown that almost all the mass of the atom sits in a tiny center called the nucleus. Electrons moved around this center, but the real weight of matter was packed into a space far smaller than anyone had imagined. That raised a new question. What exactly was inside that nucleus? It could not be a smooth ball of positive charge. Experiments were starting to show that it had structure. By the 1920s, scientists knew that the nucleus carried positive electric charge. They also knew that atoms of different elements had different masses. Hydrogen was the lightest, helium was heavier, carbon was heavier still. The positive charge in the nucleus seemed to come in units. Each element had a number called its atomic number, which matched the number of positive charges in its nucleus. That positive charge was carried by particles called protons. The proton had been identified through work on hydrogen nuclei. Hydrogen is the simplest atom. It has one electron and one positive charge in its nucleus. That positive charge behaves like a single particle. When hydrogen atoms lose their electron, the remaining nucleus is just a proton. So for a time, many scientists believed that nuclei were made only of protons and electrons, somehow packed tightly together. But there was a problem. The mass of many nuclei did not match that picture. Take helium as an example. Helium has 2 protons, so its nucleus has a charge of +2. If the nucleus contained only 2 protons and 2 electrons to balance charge, the mass would not add up correctly. The measured mass was larger than expected. There was extra mass inside the nucleus that could not be explained by protons alone. Also, if electrons were inside the nucleus, they would need to be confined in an extremely small space. Quantum mechanics showed that squeezing an electron into such a tiny region would give it huge energy, far more than what experiments showed. The mystery deepened. Something else had to be inside the nucleus. It had to carry mass, but no electric charge. It had to help explain why nuclei were heavier than the number of protons alone would suggest. For years, this unknown particle was suspected but not proven. The breakthrough came in 1932 through the work of James Chadwick. Chadwick was studying radiation produced when alpha particles struck light elements like beryllium. Earlier experiments had shown that when alpha particles hit beryllium, a very penetrating type of radiation was produced. At first, some researchers thought this radiation was made of high-energy gamma rays, which are a form of electromagnetic radiation. But the behavior of this radiation did not fit the pattern expected from gamma rays. Chadwick designed a careful experiment. he directed alpha particles at a thin sheet of beryllium and allowed the resulting radiation to strike paraffin wax, a material rich in hydrogen. When the radiation hit the wax, it knocked protons out of the hydrogen atoms. By measuring the energy of these ejected protons, Chadwick could calculate the energy of the incoming radiation. What he found did not make sense if the radiation were gamma rays. The energy transfer was too large. The only explanation that fit the data was that the radiation consisted of particles with mass nearly equal to that of a proton, but carrying no electric charge. Chadwick had discovered the neutron. The neutron solved multiple problems at once. It explained the extra mass inside nuclei. It explained how nuclei could have high mass without additional positive charge. It also removed the need to place electrons inside the nucleus. Nuclei could now be understood as combinations of protons and neutrons. The number of protons determined the element. The number of neutrons could vary, giving rise to different isotopes of the same element. With the discovery of the neutron, the basic structure of the nucleus became clearer. A nucleus is made of protons and neutrons packed tightly together in an extremely small volume. The size of this volume is hard to grasp. The typical radius of a nucleus is about 1 femtometer, which is 10 to the minus 15 meters. To understand how small that is, compare it to the size of the whole atom, which is about 10 to the minus 10 meters. The nucleus is about 100,000 times smaller in radius than the atom itself. Even though the nucleus is so small, it contains almost all the mass of the atom. If the atom were scaled up to the size of a large stadium, the nucleus would be like a small marble at the center, while the electrons would occupy the outer regions far away. Most of the atom is empty space. The density of nuclear matter, however, is enormous. If you could compress matter to nuclear density, a small amount would weigh billions of tons. The proton carries a positive electric charge equal to 1 elementary charge, often written as plus 1e. The neutron carries no electric charge, but its mass is slightly greater than that of the proton. The masses of both are close to 1 atomic mass unit. Inside the nucleus, these particles are not sitting still. They move under the influence of powerful forces. The most important of these is the strong nuclear force. The strong nuclear force acts between protons and neutrons and holds them together. Without it, the positive charges of the protons would push each other apart due to electric repulsion. The electric force between two protons is strong and acts over long distances compared to the size of the nucleus. Yet inside the nucleus, protons remain bound together. This means that another force must be stronger than the electric repulsion at very short distances. The strong nuclear force has a very short range. It acts effectively only over distances on the order of 1 femtometer, roughly the size of the nucleus itself. Within this range, it is much stronger than the electric force. But beyond this range, it drops off quickly and becomes negligible. This short range explains why the nucleus has a limited size. If the strong force acted over long distances, matter would behave very differently. Understanding the strong force required new ideas in physics. It could not be explained by the same equations that describe electric or gravitational forces. The force between protons and neutrons depends on distance and also on their internal properties. As scientists studied nuclear reactions and particle collisions, they realized that protons and neutrons are not elementary particles in the deepest sense. They have internal structure. The idea that protons and neutrons might be made of smaller parts began to gain support in the mid-20th century. High-energy experiments revealed patterns in how particles scattered off each other. These patterns suggested that protons and neutrons contain smaller point-like objects inside them. These objects are now known as quarks. The proton is made of 2 up quarks and 1 down quark. The neutron is made of 1 up quark and 2 down quarks. This means that even though the nucleus was once thought to be the final core of matter, it is not the end of the story. Inside the nucleus are protons and neutrons. Inside protons and neutrons are quarks bound together by gluons, which carry the strong interaction at a deeper level. The force that holds the nucleus together is a leftover effect of the more fundamental strong interaction between quarks. The binding energy of the nucleus is another key idea. When protons and neutrons come together to form a nucleus, the total mass of the nucleus is slightly less than the sum of the masses of the separate particles. This missing mass is not lost. It is converted into binding energy according to the equation E equals mc squared. This energy holds the nucleus together. To break a nucleus apart, you must supply energy equal to this binding energy. Different nuclei have different binding energies. Light nuclei like hydrogen have little binding energy. Medium-sized nuclei like iron have very high binding energy per particle. Heavy nuclei like uranium have lower binding energy per particle compared to iron, which is why they can release energy through nuclear fission. These details show that the nucleus is not a simple cluster of particles, but a system governed by precise energy rules. The size of the nucleus depends on the number of protons and neutrons it contains. As more particles are added, the radius increases roughly with the cube root of the number of nucleons. Even large nuclei, however, remain on the scale of femtometers. The density stays nearly constant. This uniform density suggests that nuclear matter behaves almost like an incompressible fluid at small scales. Protons inside the nucleus repel each other because they all carry positive charge. The strong nuclear force overcomes this repulsion at short distances, but as the number of protons increases, the electric repulsion grows. This is why very heavy nuclei become unstable. Beyond a certain size, the strong force can no longer fully counter the electric force, and the nucleus may undergo radioactive decay. Experiments using particle accelerators have probed nuclei by firing high-energy particles at them and studying the scattering patterns. These experiments reveal details about nuclear size, shape, and internal motion. They confirm the approximate nuclear radius of 1 femtometer and show that nucleons are packed closely together with little empty space between them inside the nucleus itself. Despite the depth of this knowledge, the nucleus is not the smallest structure in nature. It is a layer in a deeper hierarchy. First, atoms were thought to be indivisible. Then the nucleus was discovered inside the atom. Then protons and neutrons were found inside the nucleus. Then quarks were found inside protons and neutrons. Each step required new tools, new experiments, and new theory. Inside the nucleus, matter reaches extreme density and is governed by forces far stronger than anything experienced in daily life. The scale of 1 femtometer marks a boundary where classical pictures fail, and quantum rules dominate completely. The discovery of the neutron by James Chadwick was the turning point that clarified nuclear structure. It transformed the understanding of atomic mass and opened the door to nuclear physics, nuclear energy, and the study of the strong force. Scientific depth, forces, charge, and what lies beneath. Inside the nucleus, protons and neutrons are packed together at distances so small that the rules of everyday physics no longer apply. The size of this region is about 1 femtometer or 10 to the minus 15 meters. Within that space, forces act with enormous strength. The proton carries a positive electric charge equal to 1 elementary charge, written as plus 1e. This charge is a fixed property. It does not change with temperature, pressure, or environment. Every proton in the universe carries exactly the same amount of charge. That charge creates electric repulsion between protons. According to the law of electric force, 2 positive charges push each other away. The strength of this repulsion depends on the size of the charges and the distance between them. At nuclear distances, this electric force is extremely strong. If electric repulsion were the only force acting inside the nucleus, no nucleus containing more than 1 proton could exist. 2 protons placed 1 femtometer apart repel each other with a force large enough to overcome gravity by many orders of magnitude. Yet nuclei containing dozens of protons are stable. Some contain more than 90. This means that another force must be present, one that is stronger than electric repulsion at short distances. That force is called the strong nuclear force. It acts between protons and neutrons and binds them together. The strong nuclear force has a very short range. Its effective range is about 1 femtometer, roughly the size of the nucleus itself. Within this range, it is far stronger than the electric force. Beyond this distance, it drops off rapidly and becomes negligible. This short range explains why the nucleus is compact. It also explains why the force does not affect objects at larger scales. You do not feel the strong force between your hands or between two nearby objects. It operates only inside nuclei. The strong nuclear force is not a simple attraction like gravity. It depends on distance in a complex way. At extremely short distances, less than about half a femtometer, the force becomes repulsive. This prevents protons and neutrons from collapsing into each other. At slightly larger distances, around 1 femtometer, the force becomes strongly attractive. This attraction binds the particles together. The balance between short-range repulsion and slightly longer-range attraction gives the nucleus its structure and stability. To understand how this works, consider two protons inside a nucleus. They repel each other because both carry positive charge. At the same time, the strong nuclear force pulls them together. When they are about 1 femtometer apart, the strong attraction is greater than the electric repulsion. The net effect is binding. The two protons remain close. If they move too close, the short-range repulsive part of the strong force pushes them apart slightly. This balance creates a stable configuration where protons and neutrons remain bound without collapsing into a single point. Neutrons play a critical role in this balance. Although neutrons carry no electric charge, they experience the strong nuclear force just as protons do. By adding neutrons to a nucleus, the strong attraction increases without increasing electric repulsion. This helps stabilize nuclei with many protons. For light elements, the number of neutrons is often close to the number of protons. For heavier elements, more neutrons are needed to maintain stability. Without neutrons, only hydrogen would be stable. The concept of binding energy is central to nuclear physics. When protons and neutrons come together to form a nucleus, energy is released. This released energy is called binding energy. According to Einstein's equation E equals mc squared, energy and mass are related. When energy is released during the formation of a nucleus, the total mass of the nucleus becomes slightly less than the sum of the masses of the individual protons and neutrons. This difference is called the mass defect. The missing mass has been converted into binding energy. For example, if you take 2 protons and 2 neutrons and allow them to form a helium nucleus, the mass of the resulting nucleus is slightly less than the combined mass of the 4 separate particles. The difference in mass corresponds to the energy that was released when the nucleus formed. To break the nucleus apart again, you must supply exactly that amount of energy. The stronger the binding energy, the more stable the nucleus. Binding energy varies between elements. When scientists measure binding energy per nucleon, which means per proton or neutron, they find a pattern. Light nuclei have lower binding energy per nucleon. As you move to medium-sized nuclei like iron, the binding energy per nucleon increases and reaches a maximum. For very heavy nuclei, the binding energy per nucleon decreases again. This pattern explains why energy can be released in 2 different ways. Light nuclei can release energy by fusing together because the resulting nucleus has higher binding energy per nucleon. Very heavy nuclei can release energy by splitting apart because the fragments have higher binding energy per nucleon than the original nucleus. Inside the nucleus, the particles are not fixed in place like balls in a box. They move according to quantum rules. Their positions and momenta are described by wave functions. The strong force creates a potential well that confines them within the nuclear radius. Because the size of the nucleus is so small, quantum effects are dominant. The uncertainty principle plays a major role. Confining a particle to a space of 1 femtometer gives it significant momentum uncertainty. This means nucleons move with high speeds inside the nucleus. The strong nuclear force that binds protons and neutrons is not the most fundamental level of the strong interaction. Deeper inside, protons and neutrons themselves are made of smaller particles called quarks. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 1 up quark and 2 down quarks. These quarks are bound together by particles called gluons. The theory that describes this interaction is quantum chromodynamics. In quantum chromodynamics, the strong force arises from the exchange of gluons between quarks. Quarks carry a type of charge known as color charge. This is not related to visual color. It is simply a property that determines how quarks interact through the strong force. Gluons carry color charge as well, which allows them to interact not only with quarks, but also with each other. This makes the strong interaction more complex than the electric force, where photons do not carry electric charge. The force that binds quarks inside protons and neutrons is extremely strong. In fact, it becomes stronger as quarks are pulled apart. This property is known as confinement. It means quarks cannot be isolated under normal conditions. If you try to pull 2 quarks apart, the energy in the gluon field between them increases until it becomes large enough to create a new quark and antiquark pair. Instead of separating 1 quark, you end up forming new composite particles. This is why free quarks have never been observed in experiments. The strong nuclear force between protons and neutrons is a residual effect of the more fundamental force between quarks. It is similar to how molecules experience forces due to the electric interactions of their internal charges. The nucleus is held together by this residual strong force, even though the underlying mechanism operates at the quark level. Experiments in high-energy particle accelerators have provided evidence for quark structure. When protons are struck by very high-energy electrons, the scattering patterns show point-like constituents inside them. These constituents match the properties expected for quarks. The resolution of these experiments reaches down to distances of about 10 to the minus 19 meters. Within this scale, quarks appear to have no internal structure. They behave as point-like particles. This means that protons and neutrons are not fundamental. They are composite particles made of quarks bound by gluons. The nucleus, once thought to be the smallest core of matter, is itself built from smaller components. The discovery of quarks pushed the boundary of known structure deeper by several orders of magnitude. Despite this deeper layer, the behavior of nuclei can often be described without referring directly to quarks. Nuclear physics uses models where protons and neutrons are treated as particles interacting through effective forces. These models successfully predict many properties of nuclei, including energy levels, decay patterns, and reaction outcomes. However, at the most fundamental level, these nucleons are not indivisible. The interplay between electric repulsion and strong attraction defines the structure of every nucleus. If the strong force were slightly weaker, nuclei would not hold together. If it were slightly stronger, nuclear matter might collapse into denser forms. The range of about 1 femtometer sets the scale for nuclear size. The charge of the proton sets the scale for electric repulsion. The balance between these forces determines which elements can exist and which cannot. As research continues, scientists probe deeper into the structure of matter using higher energies and more precise detectors. Each new layer reveals that what once seemed fundamental is composed of smaller parts. Protons and neutrons are essential for understanding nuclei, but they are not the final step. Beneath them lie quarks and gluons, governed by quantum fields that extend throughout space. The exploration of the nucleus revealed a world where forces are immense, distances are tiny, and mass is tightly concentrated. It showed that matter is not built from solid indivisible pieces, but from dynamic systems, bound by interactions that operate at scales far beyond everyday experience. The quark revolution. By the early 1960s, particle physics was in a state of confusion. Experiments with particle accelerators had revealed a growing list of short-lived particles that appeared whenever protons were smashed into other particles at high speeds. These particles were called hadrons, and there were dozens of them. Each had a specific mass, lifetime, and electric charge. Some decayed in a fraction of a second. Others lasted slightly longer. The number of known particles kept increasing as accelerators reached higher energies. Physicists began to refer to this situation as the particle zoo because it seemed like new species were being discovered every year. There had to be order hidden beneath this apparent chaos. Patterns began to appear when the particles were grouped according to properties such as electric charge and a quantity known as strangeness, which was introduced to describe unusual decay behavior. Certain particles seemed to form families. Their masses followed regular steps. Their charges lined up in symmetrical arrangements when plotted on diagrams. This suggested that the hadrons might not be fundamental particles at all, but combinations of something simpler. In 1964, Murray Gell-Mann proposed a bold idea. He suggested that hadrons are made of smaller constituents, which he named quarks. Around the same time, George Zweig independently proposed a similar concept, referring to these constituents as aces. Both physicists were attempting to explain the patterns seen in particle data. The idea was simple but radical. Instead of dozens of fundamental particles, there might be only a few basic building blocks arranged in different combinations. Gell-Mann's proposal was based on a mathematical symmetry known as SU3, which allowed particles to be organized into groups that fit precise geometric patterns. When these patterns were drawn, they formed shapes such as hexagons and triangles in abstract space defined by quantum numbers. One famous example was the eightfold way, where 8 related particles fit into a symmetrical arrangement. This symmetry suggested that these particles could be combinations of 3 more basic entities. According to the model, quarks would combine in groups of 2 or 3 to form the known hadrons. Mesons would be made of a quark and an antiquark. Baryons, such as the proton and neutron, would be made of 3 quarks. The mathematics predicted the existence of certain particles that had not yet been observed. In 1964, a particle called the omega- was predicted as part of this symmetrical pattern. Its mass and charge were calculated from the model. In 1964, the omega- was discovered in experiments with almost exactly the predicted properties. This discovery gave strong support to the quark model. Despite this success, many physicists were skeptical. The proposed quarks had unusual properties. Their electric charges were fractions of the electron's charge, something never observed before in isolated particles. No one had ever detected a free quark. If quarks existed, why had they not been seen directly? Some researchers thought quarks might be purely mathematical tools, useful for organizing data, but not physically real. The question could not be settled by theory alone. It required experiments capable of probing inside protons and neutrons at much smaller scales than before. In the late 1960s, such experiments became possible at SLAC National Accelerator Laboratory. SLAC housed a powerful linear accelerator capable of producing very high-energy electron beams. These electrons could be directed at targets containing protons. By observing how the electrons scattered after collision, physicists could infer information about the internal structure of the proton. This technique was known as deep inelastic scattering. It differed from earlier scattering experiments in both energy and detail. In earlier experiments, scattering often revealed overall size and charge distribution. In deep inelastic scattering, the electrons carried so much energy that they could penetrate deep inside the proton. The word inelastic refers to the fact that the proton was often broken apart in the collision, producing new particles. The pattern of scattered electrons contained information about what lay inside. When high-energy electrons struck protons at SLAC in 1968, the results were surprising. If the proton were a smooth blob of charge, the scattering would follow one pattern. If it contained smaller, point-like components, the scattering would look different. The data showed sharp peaks and distributions consistent with electrons bouncing off small, concentrated centers of charge inside the proton. These centers behaved like independent particles during the brief moment of collision. The experiments were led by physicists, including Jerome Friedman, Henry Kendall, and Richard Taylor, who later received the Nobel Prize for this work. Their measurements showed that the proton contained smaller objects that carried momentum and electric charge. The scattering results could not be explained by treating the proton as a uniform object. Instead, the proton behaved as though it contained point-like constituents that absorbed and re-emitted energy during the collision. The analysis revealed that these internal constituents carried specific fractions of the proton's momentum. The pattern matched predictions from the quark model. The deep inelastic scattering experiments provided the first strong experimental evidence that quarks were not just mathematical constructs. They behaved as physical entities inside protons. Another key result from these experiments was the scaling behavior observed in the data. The structure functions measured in scattering appeared to depend on certain combinations of variables in a way predicted by theoretical work from James Bjorken. This scaling suggested that at high energies, the internal constituents acted almost like free particles during the collision. For a brief moment, the electron interacted with a single quark, as though it were isolated, even though quarks are never observed alone outside hadrons. This evidence changed the direction of particle physics. The quark model was no longer just a classification scheme, it was a description of real internal structure. Protons and neutrons were composite objects made from smaller building blocks. The idea that hadrons were fundamental particles collapsed under the weight of experimental data. The revolution extended beyond the proton. Similar scattering experiments were performed on neutrons using deuterium targets. The patterns again indicated internal point-like constituents. The behavior was consistent across different types of hadrons. The quark picture provided a unified explanation for the structure of many particles in the particle zoo. The discovery also influenced the development of quantum chromodynamics, the theory that describes how quarks interact. It became clear that the force binding quarks together had unusual properties. The scattering results hinted that the force between quarks becomes weaker at very high energies, allowing them to behave almost independently during collisions. This behavior required a new kind of field theory beyond quantum electrodynamics. As accelerators grew more powerful in the following decades, additional evidence for quark structure accumulated. Particle jets observed in high-energy collisions matched predictions from quark interactions. The patterns of particle production reflected the presence of underlying quark processes. The quark model evolved from a simple symmetry idea into a central pillar of modern particle physics. The impact of the quark revolution cannot be overstated. Before 1964, the number of supposedly fundamental particles was growing rapidly. After the quark model gained acceptance, that list shrank. Many particles once thought fundamental were reclassified as composite states. The structure of matter gained a deeper layer. Instead of atoms being the final building blocks, and instead of protons and neutrons being fundamental, the true structure extended further down. Deep inelastic scattering at SLAC provided the crucial turning point. It transformed the quark model from speculation into experimental science. High-energy electrons acted like microscopes, revealing details at distances far smaller than atomic nuclei. The scattering patterns served as fingerprints of internal structure. Each collision added data. Each dataset strengthened the case. By the early 1970s, the reality of quarks was widely accepted. Theoretical work and experimental confirmation moved forward together. New particles predicted by quark theory were discovered. The particle zoo became organized into a clear framework. What once seemed like a chaotic collection of unrelated particles became a structured system built from smaller units. Quarks, the building blocks within. Quarks are the fundamental components that make up protons and neutrons. Unlike protons or neutrons, which can exist as recognizable particles in atomic nuclei, quarks cannot be isolated on their own. They are confined permanently inside composite particles, bound together by the strong interaction. The quark model describes 6 types or flavors of quarks: up, down, charm, strange, top, and bottom. Each has a specific electric charge, mass, and behavior, and the combinations of these quarks determine the properties of the particles they form. The simplest and most familiar quarks are the up and down quarks. The proton consists of 2 up quarks and 1 down quark. The neutron is made of 1 up quark and 2 down quarks. The charges of the quarks combine to give the total electric charge of the particle. An up quark carries a charge of plus 2/3 of an elementary charge, while a down quark carries a charge of minus 1/3. Adding the charges of the quarks in a proton gives plus 1, and in a neutron, 0. These fractional charges had never been observed directly in isolation, but were inferred from the behavior of the particles they compose. The remaining quark flavors, charm, strange, top, and bottom, are heavier and less common in ordinary matter. They are typically produced only in high-energy collisions in particle accelerators or cosmic ray interactions. The discovery of these quarks expanded the understanding of matter and provided a framework to classify all known hadrons, which are particles composed of quarks. By combining 3 quarks or a quark-antiquark pair in different arrangements, virtually every observed hadron could be described. Quarks interact via the strong nuclear force, mediated by particles called gluons. Unlike photons, which mediate the electromagnetic force and do not carry charge, gluons themselves carry a type of charge known as color charge. This means that gluons can interact with each other as well as with quarks, creating a highly complex and dynamic system inside hadrons. The strong interaction is responsible for confining quarks. The closer 2 quarks are pulled apart, the stronger the force becomes, a property known as confinement. Attempting to separate quarks results not in free quarks, but in the creation of new quark-antiquark pairs, forming new hadrons instead. Quarks also exhibit a property called asymptotic freedom. At extremely short distances or very high energies, the interaction between quarks becomes weaker, allowing them to move almost independently. Deep inelastic scattering experiments, such as those conducted at SLAC, exploit this property. When high-energy electrons collide with protons, they momentarily interact with individual quarks as if the quarks were free particles. These experiments provided the first direct experimental evidence that quarks are real and point-like, rather than purely theoretical constructs. Despite their behavior appearing point-like in collisions, quarks are not necessarily dimensionless in a fundamental sense. Current experiments can probe distances down to about 1019 meters, yet no internal structure of quarks has been detected at this scale. Whether quarks have substructure or are truly elementary is still an open question in physics. Some theories beyond the standard model, such as string theory, propose that quarks may be composed of even smaller entities, though no experimental evidence exists so far. The strong binding of quarks inside protons and neutrons is what allows matter to exist in stable forms. Without this confinement, protons and neutrons would not hold together, atomic nuclei would not form, and ordinary matter as we know it could not exist. The quark model explains not only the mass and charge of nucleons, but also the complex spectrum of other hadrons, their interactions, and their decay processes. Gluons, the carriers of the strong force, continuously exchange energy between quarks. This exchange generates the internal pressure and dynamics that define hadron properties. The mass of protons and neutrons is not simply the sum of the quark masses. Most of the mass arises from the energy of quark-gluon interactions, according to Einstein's relation between energy and mass. This insight reveals that quarks themselves account for only a fraction of the total mass of matter, while the strong interaction contributes the bulk. Quarks also obey the Pauli exclusion principle in specific ways that influence particle configurations. For baryons, which contain 3 quarks, each quark must have a unique combination of quantum numbers, including color charge, spin, and flavor. This requirement explains why quarks combine in specific patterns and why certain particle states exist while others do not. The principle enforces order within the apparent chaos of the quark system. High-energy experiments have repeatedly confirmed the point-like nature of quarks. Collisions at modern particle accelerators produce jets of particles that trace the paths of quarks, showing behavior consistent with the quark model. The energy distributions, angles, and correlations of these jets match predictions from quantum chromodynamics, the theory that governs quark interactions. Quarks are consistently found to behave as if they are indivisible points, even at distances far smaller than atomic nuclei. Understanding quarks is essential not only for particle physics, but also for cosmology. The behavior of quarks in the early universe influenced the formation of matter. During the first microseconds after the Big Bang, temperatures and energies were so high that quarks and gluons existed in a free state called quark-gluon plasma. As the universe cooled, quarks combined into protons, neutrons, and eventually nuclei, forming the first elements. This process set the stage for the chemical evolution that leads to stars, planets, and life. Quarks remain a central focus of research today. Experiments continue to probe their properties, measure their interactions, and search for possible substructure. Particle accelerators such as the Large Hadron Collider push energies higher than ever, creating conditions in which new quark phenomena could appear. Understanding quarks at the deepest level is a key goal of fundamental physics, bridging the gap between matter we can see and the forces and particles that govern its structure. The study of quarks has fundamentally reshaped the view of matter. From the particle zoo of the 1950s and early 1960s to a coherent picture of 3 generations of quarks bound by gluons, physics has moved from confusion to understanding. Protons and neutrons are no longer indivisible objects. They are complex assemblies of quarks and gluons, governed by rules of quantum chromodynamics, and they form the foundation of the visible universe. Each discovery about quarks takes us closer to answering the ultimate questions. What is matter made of, and how small can its fundamental components be? The electron. Truly fundamental? Among all the particles discovered in the last century, the electron holds a unique place. It is one of the first subatomic particles to be identified, one of the simplest in terms of behavior, and yet one of the most essential components of matter. Electrons are found everywhere, in the atoms that form the air we breathe, the water we drink, the stars in the sky, and in the very circuits that power our technology. Despite their ubiquity, electrons are unlike protons or neutrons. They appear to have no internal structure, no smaller constituents, and, as far as modern experiments can tell, they are point-like. In the vast hierarchy of particles, the electron stands out as a candidate for the truly fundamental building blocks of the universe. The electron was first discovered in the late 19th century through experiments with cathode rays. Scientists like J.J. Thomson observed that these rays were deflected by electric and magnetic fields, indicating that they were composed of charged particles. The charge-to-mass ratio of these particles could be measured, and the results pointed to a particle much smaller in mass than any atom, with a negative electric charge. This particle came to be called the electron. From that moment onward, the electron became central to our understanding of electricity, chemistry, and the structure of atoms. As the 20th century progressed, the electron became a key object of study in quantum mechanics. Its behavior could be described using the wave-particle duality, where it exhibits both particle-like and wave-like properties, depending on the experiment. The Schrödinger equation successfully described electrons in atoms, predicting energy levels, spectral lines, and chemical behavior. Later, Paul Dirac formulated a relativistic equation for the electron that incorporated both quantum mechanics and special relativity. The Dirac equation predicted the electron's spin, its magnetic moment, and even the existence of antimatter in the form of the positron. Every prediction made by the Dirac equation has been confirmed to remarkable precision, reinforcing the idea that the electron is a fundamental particle. One of the most striking aspects of the electron is its apparent lack of internal structure. Experiments designed to probe smaller and smaller scales have consistently shown that electrons behave as point-like particles. Scattering experiments, where high-energy particles are fired at electrons, have been able to measure distances down to approximately 10-19 meters, yet no deviation from point-like behavior has been detected. Unlike protons and neutrons, which reveal quark substructure under similar experiments, the electron shows no evidence of internal constituents. It is as small as physics currently allows us to measure. The magnetic moment of the electron provides another window into its fundamental nature. Electrons have intrinsic angular momentum, or spin, which gives rise to a tiny magnetic field. The magnetic moment can be measured with astonishing precision, using techniques like electron spin resonance and penning traps. Experiments have determined the electron's magnetic moment to over 10 decimal places, making it one of the most precisely measured quantities in all of physics. The agreement between experimental measurements and theoretical predictions, calculated using quantum electrodynamics, is extraordinary. The precision of these measurements leaves little room for hidden substructure. Any internal components would alter the magnetic moment in measurable ways, yet no discrepancies have been observed. Electrons are also unique in that they are elementary according to the standard model of particle physics. The standard model classifies all known particles into two broad categories: fermions, which make up matter, and bosons, which mediate forces. Electrons belong to the fermion family, specifically the lepton subgroup. Unlike quarks, which experience the strong force and combine into protons and neutrons, electrons do not participate in the strong interaction. They interact via the electromagnetic force, the weak force, and gravity. Their simplicity and lack of strong interactions make them ideal candidates for studying fundamental physics. Despite the simplicity suggested by the standard model, electrons are not inert or trivial. They exhibit complex behavior in the presence of forces and fields. Their quantum properties underlie chemistry, solid-state physics, and even biological processes. Electrons form chemical bonds through interactions with other electrons and nuclei. They move through conductors and semiconductors, giving rise to electric currents and enabling modern technology. Yet, at the most fundamental level, each electron behaves identically to every other electron in the universe. Its mass, charge, and spin are fixed constants. There is no experimental evidence for internal structure that would differentiate one electron from another. High-energy particle collisions have further tested the electron's fundamental nature. In electron-positron colliders, electrons are accelerated to near light speed and smashed together with their antiparticles. These collisions produce showers of particles and can probe distances far smaller than atomic nuclei. Throughout decades of experiments, electrons consistently behave as point-like particles. No scattering pattern has suggested an internal structure or compositeness. Any substructure, if it exists, must be at distances smaller than current experimental limits, far beyond what even the most powerful accelerators can probe today. The precision of electron measurements also plays a critical role in testing fundamental physics. Quantum electrodynamics, the theory describing the interaction of electrons with electromagnetic fields, relies on the electron's point-like nature. The success of QED in predicting phenomena such as the Lamb shift, the anomalous magnetic moment, and scattering cross-sections is intimately tied to the electron's elementary status. Any deviation from point-like behavior would introduce measurable corrections to these effects. The absence of such deviations strengthens the case for the electron's fundamental nature. Electrons also define the structure of atoms and matter itself. In every atom, electrons occupy energy levels around the nucleus, determining chemical properties and interactions. The arrangement of electrons in shells explains the periodic table and the behavior of elements. Chemical bonds, conductivity, magnetism, and light emission all depend on electron behavior. The fact that all electrons are identical ensures the reproducibility of these phenomena across the universe. The properties of electrons are universal constants, linking quantum physics with chemistry, materials, science, and technology. The electron's point-like nature has profound implications for the limits of physical measurement. current experiments have pushed sensitivity to about 1019 meters, roughly 100,000th the radius of a proton. At these scales, electrons still show no signs of size or internal structure. Physicists refer to this as elementary, meaning that electrons cannot be divided into smaller constituents according to present knowledge. The electron represents a boundary where the concept of substructure might cease, at least within the experimental reach of modern physics. The question of whether the electron is truly fundamental is still open in principle. Some theories beyond the Standard Model suggest that at extremely high energies, electrons might be composed of more basic objects, sometimes envisioned as tiny vibrating strings. However, such theories remain speculative and currently untestable. In the absence of experimental evidence, the electron is treated as a fundamental particle. Its simplicity, stability, and lack of internal components make it the cornerstone of our understanding of matter. Electrons are also critical in testing the laws of physics themselves. Precision measurements of the electron's properties provide some of the most stringent tests of the Standard Model. Any discrepancy between theory and experiment could hint at new physics. So far, the electron has behaved exactly as predicted, confirming the accuracy of current theories. Its interactions, magnetic moment, and response to external fields match theoretical calculations to remarkable precision. The discovery of the electron, the development of quantum mechanics, and the confirmation of its point-like nature mark one of the great achievements in the history of science. From cathode ray experiments to modern high-energy colliders, the electron has been probed more deeply than almost any other particle. Unlike protons or neutrons, it has no detectable substructure. Its mass, charge, and spin are constants of nature, identical for every electron in the universe. The Standard Model, the current map of reality. The Standard Model is the framework physicists use to describe the fundamental constituents of matter and the forces through which they interact. It organizes all known elementary particles into a coherent structure, capturing patterns in nature that range from the tiniest scales of quarks and leptons to the interactions that shape the universe itself. Unlike classical physics, which deals with macroscopic objects, the Standard Model operates at scales far smaller than atoms, where quantum mechanics governs behavior and probabilities replace certainty. Within the Standard Model, particles are grouped into three main categories: quarks, leptons, and gauge bosons. There are 6 flavors of quarks: up, down, charm, strange, top, and bottom. Each quark carries properties such as electric charge, mass, and color charge, which determines how they interact via the strong nuclear force. Quarks never exist freely in nature. They are confined into composite particles like protons and neutrons, and their combinations explain the rich spectrum of hadrons observed in particle experiments. Leptons are the second category, also numbering 6: the electron, muon, tau, and their associated neutrinos. Unlike quarks, leptons do not experience the strong force. Their interactions are limited to the weak force, electromagnetism for the charged leptons, and gravity. Neutrinos are particularly elusive. They interact so weakly with matter that billions pass through every square centimeter of your body every second without leaving a trace. Despite this, neutrinos play critical roles in astrophysics, such as in supernovae and the fusion processes that power stars. The third category, gauge bosons, mediates the fundamental forces. The photon carries the electromagnetic force, governing interactions between charged particles and enabling light, electricity, and magnetism. The gluon carries the strong force, binding quarks together inside protons, neutrons, and other hadrons. The W+ and W bosons and the Z boson mediate the weak nuclear force, responsible for certain types of radioactive decay and neutrino interactions. The discovery of these bosons was a major triumph of particle physics in the late 20th century, providing confirmation for the electroweak unification, which combines the electromagnetic and weak forces into a single theoretical framework. The Higgs boson is the most recent addition to the Standard Model and serves a unique purpose. Unlike the other particles, the Higgs does not mediate a force, but instead provides a mechanism by which other particles acquire mass. The Higgs field pervades all space, and as particles interact with this field, they acquire inertia. Particles that couple strongly to the Higgs field gain more mass. Those that interact weakly remain lighter. The Higgs boson is an excitation of this field, analogous to a ripple in a pond. Its existence was theorized in the 1960s, but remained unconfirmed for decades. After years of effort, the Higgs boson was finally detected at CERN in 2012. Using the Large Hadron Collider, scientists collided protons at unprecedented energies, creating conditions that allowed the fleeting Higgs boson to appear. Its presence was inferred from the particles into which it decayed, and the statistical significance of the results exceeded the threshold required for a discovery. This achievement confirmed the mechanism for mass proposed decades earlier and completed the particle roster of the Standard Model. The discovery also validated theoretical calculations regarding symmetry breaking, a concept central to modern quantum field theory. One of the remarkable outcomes of the Standard Model is that all elementary particles studied so far show no measurable size. Quarks, leptons, and gauge bosons behave as point-like objects in scattering experiments. High-energy collisions, such as those at the Large Hadron Collider, probe distances far smaller than atomic nuclei, down to scales of 10-19 meters, without detecting any internal structure. Even the electron, previously thought of as indivisible, conforms to these observations. The Higgs boson itself is also consistent with being a point particle. Current experimental limits suggest that if these particles have any spatial extent, it is smaller than our most sensitive instruments can detect. However, the Standard Model is not a complete description of reality. It explains the behavior of known particles and their interactions remarkably well, yet it leaves unanswered questions. For instance, the model does not include gravity in a quantum framework, which means it cannot describe how particles behave at scales where both quantum effects and gravitational forces are significant. Similarly, it does not explain dark matter or dark energy, which make up most of the mass-energy content of the universe. Physicists know that new physics must exist beyond the Standard Model to address these gaps. The Standard Model also provides a blueprint for understanding how the universe evolved. In the earliest moments after the Big Bang, temperatures and energies were so high that particles constantly transformed from one type to another. Quarks and gluons existed freely in a quark-gluon plasma. As the universe cooled, quarks combined into protons and neutrons, and nuclei formed. Leptons played essential roles in mediating energy balance and driving particle interactions. The Higgs field, ever present, gave mass to particles at the right moment, allowing the formation of stable atoms and eventually stars, galaxies, and planets. Experiments continue to probe the Standard Model with ever-increasing precision. Particle accelerators measure properties such as lifetimes, decay modes, and cross-sections, searching for deviations that could indicate new physics. Neutrino observatories study oscillations and mass differences. Colliders investigate rare processes that occur only under extreme conditions. Even tiny discrepancies, like the anomalous magnetic moment of the muon, spark intense interest because they may hint at phenomena not captured by the Standard Model. The Standard Model also provides a framework for predicting new particles and interactions. For decades, physicists used its symmetries and mathematical structure to guide experimental searches. Predictions such as the top quark, the tau neutrino, and the Higgs boson were confirmed experimentally after careful design and observation. This predictive power underscores the robustness of the model, while simultaneously motivating searches for physics beyond it. While quarks, leptons, and bosons form the core of the Standard Model, their interactions are governed by quantum fields. Each particle is an excitation of a field that fills all space. The photon arises from the electromagnetic field, gluons from the color field, and the Higgs boson from the Higgs field. This field-based description allows physicists to calculate interaction probabilities energy levels, and particle production in collisions. The mathematical formalism captures phenomena from the smallest scales measured to the high energies present in cosmic events. Despite its successes, the Standard Model points toward deeper questions. Why do particles have the masses they do? Why do quarks and leptons exist in 3 generations with similar properties but different masses? Why is the universe dominated by matter rather than antimatter? How small can physics even go? The Planck scale. At the turn of the 20th century, Max Planck made a discovery that would redefine the limits of physics. While studying blackbody radiation, he realized that energy is not continuous, but comes in discrete units called quanta. This insight laid the foundation for quantum mechanics, but Planck's work also led to a set of fundamental units that define the scales at which nature operates. Among these, the Planck length represents the smallest meaningful unit of length according to our current understanding of physics. It is an extraordinarily tiny scale, many orders of magnitude smaller than anything we can measure with present-day technology. The Planck length is approximately 1.616 x 1035 meters. To put this in perspective, a proton has a size of about 1015 meters. The Planck length is 20 orders of magnitude smaller, a scale so tiny that our conventional notions of distance, size, and space itself may not apply. It is not a quantity we measure in laboratories. No experiment has ever probed distances anywhere near this small. Instead, the Planck length is derived from 3 fundamental constants of nature: the gravitational constant, g, the speed of light in vacuum, c, and the reduced Planck constant, h. By combining these constants in a precise formula, Planck revealed a natural scale at which gravity and quantum mechanics intersect. The derivation of the Planck length begins with dimensional analysis. The gravitational constant describes the strength of gravity, a force we are familiar with on the scale of planets, stars, and galaxies. The speed of light sets the maximum speed at which information and energy can travel. The reduced Planck constant governs the scale at which quantum effects become significant. By arranging these constants into a combination that yields dimensions of length, we obtain the Planck length, L_P equals sine skirt frac h bar g c cubed. This formula expresses a deep connection between the fundamental forces of the universe. It suggests that there is a scale at which both gravity and quantum mechanics become equally important. At distances larger than the Planck length, classical notions of space and time work well, and our current theories, such as general relativity and quantum field theory, make accurate predictions. But below the Planck length, these theories are expected to break down. The smooth continuous fabric of spacetime, as described by Einstein, may no longer exist in the form we understand. Instead, space and time might be discrete, fluctuating, or subject to entirely new rules dictated by quantum gravity. Quantum gravity is the theoretical framework that seeks to describe physics at scales near the Planck length. At such extreme scales, the gravitational effects of particles with tiny masses become comparable to quantum effects. In our everyday world, gravity is incredibly weak at the scale of subatomic particles, so quantum mechanics dominates. But as we approach the Planck scale, gravitational forces become significant even for elementary particles, and the interplay between quantum uncertainty and spacetime curvature cannot be ignored. Physicists expect that at this level, spacetime may lose its classical meaning. Distances, durations, and even causality could behave in ways that defy conventional logic. One reason the Planck scale is so inaccessible is the enormous energy required to probe it. According to quantum mechanics, probing smaller distances requires higher energy particles. To reach the Planck length, the required energy approaches the Planck energy, approximately 1.22 x 1019 giga electron volts. This is far beyond the reach of any current or foreseeable particle accelerator. For comparison, the Large Hadron Collider, the most powerful collider built, operates at energies of a few tens of tera electron volts, roughly 15 orders of magnitude lower than the Planck energy. This gap underscores why the Planck length remains a theoretical concept rather than an experimentally accessible scale. Despite its inaccessibility, the Planck length has profound implications for physics. It sets a natural limit on the smallest meaningful distance in the universe. Any attempt to define a length smaller than this may lose physical significance because quantum fluctuations of spacetime become dominant. In other words, the very concept of distance may be meaningless below the Planck length. Traditional notions of geometry and continuity, which work well at human scales and even at atomic scales, may fail. Space might be granular, discrete, or governed by probabilistic rules rather than deterministic ones. The idea that spacetime may be quantized at the Planck scale arises naturally from combining quantum mechanics and general relativity. General relativity describes gravity as the curvature of spacetime caused by energy and mass. Quantum mechanics introduces uncertainty, meaning that energy and momentum cannot be defined with absolute precision. When trying to measure a distance smaller than the Planck length, the energy required would distort spacetime so significantly that the measurement itself becomes meaningless. This suggests a fundamental limit. Distances below the Planck length cannot be probed or defined in any conventional sense. Various approaches to quantum gravity attempt to describe the Planck scale in different ways. String theory, for instance, proposes that all particles are excitations of tiny one-dimensional strings. These strings have lengths comparable to the Planck length, making them the fundamental building blocks of reality. Loop quantum gravity, on the other hand, treats spacetime itself as composed of discrete loops or networks, with areas and volumes quantized in units related to the Planck scale. Both approaches highlight that the Planck length is not just a number, but a window into a regime where our current understanding of physics breaks down. Another consequence of the Planck scale is related to black holes. Black holes can, in principle, be tiny, with masses approaching the Planck mass. At this scale, quantum effects on the curvature of spacetime become essential. The smallest black holes, sometimes called Planck scale black holes, would have radii on the order of the Planck length. Theoretical studies suggest that such objects could provide clues about how quantum mechanics and gravity combine, offering insights into a theory of everything. While no Planck scale black holes have been observed, the possibility exists in high-energy environments such as the early universe or hypothetical particle collisions far beyond current technology. Time at the Planck scale is also expected to behave differently. Just as distances may lose classical meaning, intervals of time shorter than the Planck time, approximately 5.39 x 1044 seconds, may be impossible to define. The Planck time is the duration it takes light to travel one Planck length. Below this interval, the concepts of before and after may no longer apply in the usual sense. The fabric of spacetime itself could fluctuate violently, with space and time emerging only as averages over larger scales. This challenges the very foundation of physics, suggesting that space and time are not fundamental entities, but emergent properties. The Planck scale also sets limits on energy density. Concentrating enough energy in a tiny volume to probe sub-Planck distances could create a black hole, preventing any measurement. This is sometimes referred to as the black hole barrier. Trying to measure below the Planck length would produce a gravitational collapse, hiding the structure behind an event horizon. This natural limit emphasizes that the Planck length is not merely a mathematical curiosity, but a fundamental boundary dictated by the interplay of quantum mechanics and gravity. Although direct experiments at the Planck scale are impossible with current technology, physicists explore its implications indirectly. Cosmic phenomena such as the cosmic microwave background, high-energy cosmic rays, and gravitational waves provide clues about physics at extreme scales. For example, the behavior of black holes, neutron stars, and the earliest moments of the universe may reflect principles that operate near the Planck scale. By studying these phenomena, scientists hope to constrain theories of quantum gravity and understand how spacetime behaves in regimes far beyond human-scale measurements. Mathematical models at the Planck scale also have practical consequences for theoretical physics. Concepts like renormalization, quantum field theory divergences, and the unification of forces often rely on understanding physics at very small distances. The Planck length acts as a natural cutoff, indicating where classical concepts fail and where new physics must emerge. Without such a scale, certain calculations in high-energy physics would lead to infinite results, suggesting inconsistencies in the theory. The Planck scale is also deeply connected to fundamental constants and natural units. By expressing quantities in Planck units, physicists can work with numbers of order 1, simplifying equations and highlighting relationships between forces and particles. For instance, Planck energy, Planck time, and Planck mass all relate to fundamental constants in the same way that Planck length does. These units provide a framework to explore extreme conditions and unify different aspects of physical theory. Philosophically, the Planck length challenges the idea that space and time are continuous. For centuries, geometry was assumed to be infinitely divisible, but quantum gravity suggests a limit to divisibility. This has implications for understanding the structure of the universe at its most fundamental level. If space-time is discrete, then questions about the nature of points, distances, and causality must be re-examined. Physics at the Planck scale may reveal that the smooth continuum we perceive is an emergent phenomenon, arising from a deeper, granular reality. While no experiment has yet reached the Planck scale, the concept guides theoretical exploration. It informs string theory, loop quantum gravity, and other approaches attempting to unify quantum mechanics with general relativity. It defines the scale at which new principles must apply, and provides a target for thought experiments, such as hypothetical Planck scale accelerators or black hole collisions. It also sets the stage for understanding the earliest moments of the universe, when all forces may have been unified and distances approached the Planck length. The Planck scale represents the ultimate frontier of physical measurement. Derived from the constants of nature, g, c, and h, it defines the smallest meaningful length, far smaller than the scales accessible by any experiment. Below this scale, spacetime may no longer have classical meaning. Quantum gravity dominates, and conventional physics breaks down. While we cannot directly probe this regime, the Planck length informs our understanding of the universe, guiding theoretical frameworks and shaping the search for a deeper understanding of reality. It marks the boundary between what can be described by current theory and what remains hidden, pointing toward a new layer of physics where space, time, and matter merge in ways yet to be fully understood. Is spacetime itself quantized? Modern physics has long treated spacetime as a smooth, continuous fabric, stretching seamlessly in all directions, curving under the influence of mass and energy. General relativity describes gravity as the curvature of this fabric, producing effects that we can measure from falling objects on Earth to the motion of galaxies across billions of light-years. Quantum mechanics, on the other hand, shows us that at very small scales, nature behaves probabilistically, with particles and fields exhibiting uncertainty, discreteness, and fluctuations. Reconciling these two pillars of physics, relativity and quantum mechanics, leads to profound questions about the nature of spacetime itself. Is it truly smooth, or is it fundamentally granular, composed of discrete units too small for us to directly observe? One of the most promising frameworks addressing this question is loop quantum gravity. Loop quantum gravity, or LQG, begins with the idea that spacetime is not continuous but made of finite, discrete elements. It treats space not as an infinitely divisible continuum, but as a network of tiny loops, interconnected in a vast lattice-like structure. These loops are quantum excitations of the gravitational field, and they form the building blocks of space itself. In this picture, distances, areas, and volumes are quantized. They come in specific, indivisible units determined by the properties of these loops. The concept of quantized space in LQG arises from applying the principles of quantum mechanics directly to the geometry of spacetime. Instead of quantizing particles within a fixed background, as in standard quantum field theory, LQG quantizes the geometry itself. Mathematically, space is represented as a spin network, a graph whose edges and nodes carry quantum numbers corresponding to areas and volumes. The spin network evolves over time according to precise rules, producing a dynamic quantum description of spacetime. Each node in the network can be thought of as a chunk of space, with discrete volume, and the edges connecting nodes define quantized areas. In loop quantum gravity, the smallest possible units of area and volume are proportional to the Planck length squared and cubed, respectively. This ties the theory directly to the Planck scale, the scale at which quantum gravity effects are expected to dominate. The Planck length is around 1.616 x 1035 meters, far smaller than anything accessible in laboratory experiments. Yet LQG provides a concrete mathematical structure that allows physicists to explore what spacetime might look like at such extreme scales. According to the theory, you cannot meaningfully subdivide space below these fundamental units. Any attempt to do so is prohibited by the quantization rules. Loop quantum gravity also predicts that time may be discrete, though this aspect is less directly formulated. Just as space is composed of individual quanta, the evolution of the spin network can be interpreted as a sequence of discrete time steps at the Planck scale. Events that appear smooth and continuous at macroscopic scales emerge from a vast number of discrete updates at the quantum level. The passage of time, in this framework, is an emergent phenomenon arising from the evolution of quantum geometry. One of the remarkable consequences of quantized spacetime is its implications for the nature of singularities. In general relativity, black holes and the Big Bang are described as singularities, points where densities become infinite and classical physics breaks down. Loop quantum gravity suggests that quantization of spacetime may resolve these singularities. Since volumes and areas cannot shrink below a minimum quantum, the infinite densities predicted by classical theory are avoided. Instead, black holes may have a finite core, and the early universe may have passed through a quantum bounce rather than a singular beginning. These predictions provide testable consequences, at least in principle, though confirming them remains a challenge. Mathematically, loop quantum gravity is formulated using techniques called canonical quantization. The classical variables describing geometry and general relativity are rewritten in terms of connection variables and conjugate momenta. The resulting quantum theory uses operators to represent areas and volumes, with discrete eigenvalues corresponding to quantized measurements. The spin networks encode these eigenvalues, providing a graphical representation of space at the smallest scales. Calculations show that the spectrum of possible areas and volumes is discrete, confirming the central idea that space is fundamentally granular. Another aspect of LQG is its approach to gravity. In this framework, gravity is not a force propagating through a background spacetime, but an emergent property of the quantum geometry itself. Curvature arises from the way loops are connected and evolve. The interactions of these loops produce the effects we associate with gravitational attraction. This view is radically different from classical physics, where gravity is a smooth curvature of a continuous manifold. In LQG, curvature emerges from the combinatorial structure of loops, a fundamentally quantum phenomenon. Loop quantum gravity also has implications for the propagation of light and particles through space. Since space is composed of discrete units, photons traveling over vast distances might experience subtle deviations from classical predictions. These deviations could manifest as energy-dependent variations in the speed of light, or tiny distortions in the behavior of high-energy cosmic rays. Observations of gamma-ray bursts and other astrophysical phenomena are used to place constraints on such effects. So far, no deviations have been detected, but the limits provide important information about the possible structure of quantum spacetime. Cosmology is another arena where loop quantum gravity offers insights. In loop quantum cosmology, a simplified version of LQG applied to the universe as a whole, the Big Bang singularity is replaced by a quantum bounce. The universe contracts to a minimum volume determined by the quantized geometry and then expands again, potentially cyclically. This model predicts subtle imprints in the cosmic microwave background radiation, which could, in principle, be observed. While direct confirmation is challenging, these predictions make the theory scientifically meaningful rather than purely speculative. The quantization of spacetime also affects black holes. In LQG, the event horizon of a black hole can be modeled as a collection of discrete patches, each corresponding to a quantum of area. The entropy of the black hole, which measures the number of microscopic states compatible with a given macroscopic configuration, is then proportional to the number of these patches. This reproduces the famous Bekenstein-Hawking relation between entropy and area, connecting quantum gravity with thermodynamics. It also provides a framework to study Hawking radiation, information loss, and other quantum aspects of black holes. Loop quantum gravity does not require extra dimensions or exotic particles. It focuses entirely on applying quantum principles to the known structure of spacetime. This sets it apart from other approaches to quantum gravity, such as string theory, which introduces additional spatial dimensions and one-dimensional fundamental objects. LQG works within the framework of general relativity, taking seriously the idea that spacetime itself is the dynamic entity to be quantized. Despite its elegance, loop quantum gravity faces significant challenges. Calculations in full, realistic settings are complex, and connecting the theory with low-energy physics is difficult. Recovering classical spacetime as an approximation of the discrete structure involves understanding how enormous numbers of quantum loops combine to produce smooth space and time at macroscopic scales. While progress has been made, a complete solution is still an active area of research. Experimental confirmation of LQG remains elusive. Probing the Planck scale structure directly is far beyond current technology. Indirect tests, such as searching for energy-dependent effects in high-energy astrophysical photons or subtle deviations in the behavior of black holes, are ongoing. Observations of the early universe, gravitational waves, and cosmic ray propagation provide constraints, but no definitive evidence yet confirms the quantization of spacetime. The theory, however, makes precise predictions, making it a testable and falsifiable framework rather than a purely philosophical proposal. Loop quantum gravity also interacts with other areas of physics. It provides insights into quantum field theory in curved spacetime, the nature of vacuum fluctuations, and the relationship between geometry and information. Concepts from LQG have inspired new approaches to understanding the holographic principle, where information about a volume of space may be encoded on its boundary. These connections show that quantized spacetime has implications beyond gravity, influencing our understanding of information, entropy, and fundamental physics at multiple scales. The conceptual shift introduced by LQG is profound. If space and time are discrete, then the universe is fundamentally digital at its core. The continuous spacetime of general relativity emerges as an approximation, much like a high-resolution image appears smooth to the eye, even though it is made of individual pixels. This perspective changes the way we think about the universe, causality, and the limits of measurement. It also suggests that the ultimate building blocks of reality may not be particles or strings, but the loops and networks that define the structure of space itself. The scale at which these effects occur is intimately tied to the Planck length. Each loop, each quantum of area and volume, is on the order of 1035 meters. To observe individual loops directly would require energies and resolutions far beyond what is technologically feasible. Nevertheless, the implications of such a discrete structure can manifest in subtle ways at larger scales, guiding the search for phenomena that could reveal the granular nature of space. String theory, the universe as vibrating strings. String theory approaches the question of fundamental reality from a radically different perspective. Whereas loop quantum gravity seeks to quantize spacetime itself, string theory proposes that the elementary constituents of the universe are not point particles at all, but one-dimensional objects called strings. These strings are incredibly tiny, with lengths comparable to the Planck length, around 10 to 35 meters. Each string can vibrate in different modes, and these vibrational patterns give rise to the particles and forces we observe. An electron, a quark, or even a photon is simply a particular way a string vibrates. The development of string theory began in the late 1960s as a model for the strong nuclear force, but it was soon realized that it could describe more than just hadrons. Early formulations showed that string vibrations naturally included a particle with properties consistent with the graviton, the hypothetical quantum of gravity. This discovery suggested that string theory could unify all forces, including gravity, under a single framework. Unlike quantum field theories of point particles, string theory inherently avoids certain infinities because the extended nature of strings smooths interactions at extremely small scales. Strings come in different types, such as open strings with two ends and closed strings that form loops. The type of string and its vibrational pattern determines the particle it represents, including its mass, charge, and spin. Interactions between particles in this view correspond to strings splitting, joining, and vibrating together. The mathematical structure of string theory requires extra dimensions of space beyond the familiar three. Depending on the version of string theory, there may be 10 or even 11 dimensions, with the additional dimensions compactified into shapes so small they are undetectable at ordinary scales. String vibrations are quantized, much like the harmonics on a guitar string. Each mode of vibration corresponds to a distinct particle, and the energy associated with that vibration determines the particle's mass. The richness of the vibrational spectrum allows string theory to produce the wide variety of particles observed in nature, including all quarks, leptons, and gauge bosons. The graviton emerges naturally as a closed string vibration, providing a built-in mechanism for quantum gravity. An essential aspect of string theory is that the strings themselves are not directly observable. Their scale is so small that no current or foreseeable experiment can probe them directly. Instead, physicists study the implications of string theory for particle interactions, symmetries, and cosmology. The theory predicts relationships between particle masses, coupling constants, and interactions, although many of these predictions are difficult to test due to the energy scales involved. Despite the lack of direct experimental confirmation, string theory provides a mathematically consistent framework that unifies quantum mechanics and general relativity. The extra dimensions required by string theory are compactified into complex geometrical shapes called Calabi-Yau manifolds. These tiny, curled-up dimensions influence the vibrational modes of strings, thereby determining the properties of particles in the observable three-dimensional world. Different shapes produce different spectra of particles, which means the structure of the extra dimensions directly affects physics at low energies. Understanding these compactified dimensions is central to making string theory consistent with the universe we see. String theory also allows for dualities, surprising mathematical equivalences between seemingly different theories. For example, T-duality relates string theories in large and small compactified dimensions, while S-duality connects strongly interacting strings to weakly interacting ones. These dualities reveal deep symmetries in the mathematics of the theory, suggesting that different formulations of string theory may be aspects of a single underlying framework. This has led to the development of M-theory, a broader structure that encompasses all known string theories and includes 11-dimensional supergravity. Supersymmetry is another fundamental component of string theory. Supersymmetry postulates that every known particle has a superpartner with different spin properties. This symmetry helps to cancel mathematical inconsistencies, such as infinities, and provides candidates for dark matter. While superpartners have not yet been observed experimentally, they are a natural consequence of the theoretical structure. The interplay between supersymmetry, extra dimensions, and string vibrations creates a rich and intricate framework that could describe all fundamental physics. String theory also has cosmological implications. In the early universe, when energies were extremely high, strings could stretch, vibrate, and interact in complex ways. The dynamics of strings could influence inflation, the distribution of matter, and the formation of large-scale structures. Certain models suggest that cosmic strings, extended one-dimensional defects left over from phase transitions in the early universe, might exist and leave observable imprints, such as gravitational lensing patterns or gravitational waves. These signatures, if detected, could provide indirect evidence supporting string theory. Another consequence of strings being one-dimensional is that they soften interactions at extremely short distances. Point particles in quantum field theory can produce infinities when they interact at zero distance, requiring renormalization procedures. Strings, by contrast, have finite length, so interactions are naturally spread over a small but finite distance. This property resolves certain mathematical divergences and allows string theory to describe gravity consistently with quantum mechanics. Despite its elegance, string theory faces challenges. The energy scale at which strings would be directly observable is far beyond current experimental capabilities. While the Large Hadron Collider can probe scales down to about 10-19 meters, strings are expected to exist near the Planck length, 10-35 meters. This immense gap means that direct detection of strings is impossible with present technology. As a result, string theory is largely constrained by internal consistency, mathematical structure, and indirect implications rather than direct experimental proof. String theory also produces a vast landscape of possible universes, each corresponding to different shapes of compactified dimensions and different parameters for physical laws. This multiplicity of possibilities has led to philosophical debates about predictability and testability. In principle, only a subset of these vacua would correspond to a universe like ours, but identifying which one requires understanding the dynamics of the compactified dimensions and the mechanisms that select particular configurations. Interactions in string theory occur through the splitting and joining of strings. For example, a closed string representing a graviton can interact with open strings representing matter particles, transmitting gravitational effects. The strength and nature of these interactions are determined by the properties of the strings and the geometry of the extra dimensions. This framework allows the unification of all forces in a single consistent description, something that has eluded other approaches to fundamental physics. String theory also predicts new forms of matter and phenomena at high energies. Brains, higher dimensional analogues of strings, can exist in various dimensions and influence physics in the observable universe. Our entire universe could, in principle, be a three-dimensional brain embedded in a higher dimensional space, with gravity leaking into the extra dimensions. Such models can explain why gravity appears weaker than the other forces and provide frameworks for understanding cosmology and black hole physics. Although experimental confirmation is lacking, string theory has influenced many areas of physics beyond fundamental particles. Insights from string theory inform black hole thermodynamics, holography, and condensed matter physics. The ADIS-CFT correspondence, for example, relates a string theory in a higher dimensional space to a quantum field theory on its boundary. This duality has provided powerful tools for studying strongly interacting systems and has led to advances in understanding phenomena such as superconductivity, quark-gluon plasmas, and entanglement entropy. The vibrational modes of strings are at the heart of the theory. Each mode corresponds to a particle with specific properties. Low-energy vibrations produce familiar particles like electrons, quarks, and photons, while high-energy excitations produce massive, exotic particles that exist only at extreme scales. The richness of this spectrum allows string theory to incorporate all known particles and forces while predicting new possibilities. The graviton, the gauge bosons of the Standard Model, and even the Higgs boson can all be interpreted as manifestations of different string vibrations. Supersymmetric string theories also naturally incorporate fermions and bosons in a unified framework. This means that matter and forces emerge from the same underlying objects, providing a conceptual unification that is difficult to achieve in point-particle approaches. The vibrational patterns encode the spin, charge, and other quantum numbers, linking the geometry of the extra dimensions with the properties of observable particles. The Planck scale length of strings ensures that the effects of string structure are negligible at ordinary scales. This is why particle experiments, such as those at the LHC, observe electrons, quarks, and photons as effectively point-like. Only at energies approaching the Planck scale would the extended nature of strings become apparent. Until technology can probe such energies, string theory remains a mathematically compelling but experimentally unverified description of the deepest structure of matter. String theory also addresses conceptual issues in quantum gravity. By replacing point particles with extended strings, it avoids singularities and provides a framework in which gravity is naturally incorporated. It also suggests that spacetime itself may be emergent, arising from the interactions and vibrations of strings and branes. In this view, space and time are not fundamental, but derive from the underlying dynamics of the strings linking geometry, quantum mechanics, and gravity in a unified description. Mathematical consistency requires that string theory exists in higher dimensional spacetimes, with the exact number depending on the type of string theory. These extra dimensions are compactified and influence low-energy physics in subtle ways. The smallest measurable distance ever probed. Collider physics has transformed our understanding of the microscopic universe. For decades, particle accelerators have allowed scientists to probe distances far smaller than any microscope could resolve, revealing the building blocks of matter and the forces that govern them. The fundamental question guiding these experiments is deceptively simple. How small can we see? How far can we push our instruments before nature itself refuses to reveal smaller structures? Modern colliders, particularly the Large Hadron Collider, have brought us closer than ever to the limits of measurable distance, approaching scales near 1019 meters. The Large Hadron Collider, or LHC, located near Geneva on the Franco-Swiss border, represents the pinnacle of collider technology. Its 27-kilometer ring accelerates protons to energies of 6.5 to 7 tera-electron volts, TeV, per beam, producing collisions with center of mass energies up to 1314 TeV. When two protons collide at these energies, the internal constituents, the quarks and gluons, interact at incredibly short distances. In particle physics, the resolution of a collision is related to the energy involved. Higher energy collisions allow probing of smaller distances because, according to the principles of quantum mechanics, the wavelength associated with the momentum of a particle decreases as energy increases. This relationship is often expressed using the de Broglie wavelength formula, where the effective resolution is inversely proportional to momentum. In practice, the LHC collisions reach effective resolution scales on the order of 1019 meters, 100,000 times smaller than the radius of a proton, and 1,000,000 times smaller than atomic nuclei. At these distances, quarks and electrons, which were once thought to potentially contain internal structure, appear point-like. Decades of high-energy experiments, from ESALAC to Fermilab, have reinforced this conclusion. Despite the extraordinary energies achieved, no deviation from point-like behavior has been observed, and no substructure has emerged within these fundamental particles. The experiments at the LHC rely on sophisticated detectors to reconstruct collision events with extreme precision. Detectors such as ATLAS and CMS are multi-layered instruments capable of tracking the paths of charged particles, measuring energies of photons and hadrons, and identifying decay products of heavy particles like the Higgs boson. In each collision, thousands of particles can emerge, creating an event that must be disentangled to identify underlying processes. By analyzing millions of such events, physicists can test whether quarks or electrons exhibit deviations from expected behavior. Any substructure would appear as discrepancies in scattering patterns, energy distributions, or the emergence of unexpected resonances. The point-like nature of quarks and electrons is confirmed through high-energy scattering experiments. Deep inelastic scattering, historically conducted at SLAC in the 1960s, provided the first evidence that protons contain point-like constituents, which we now identify as quarks. Subsequent experiments at higher energies refined our measurements, revealing the internal distribution of momentum among quarks and gluons, and confirming that the quarks themselves show no measurable size down to scales of about 1019 meters. Similarly, electrons, tested in both collider experiments and high-precision scattering studies, show no measurable radius. These results are crucial because they constrain models that propose substructure, such as preon theories, where quarks and leptons would be composed of smaller, more fundamental particles. High luminosity is a key factor in probing smaller distances. The LHC has undergone upgrades to increase luminosity, effectively increasing the number of collisions per second. High luminosity allows physicists to observe extremely rare processes that might reveal new physics. For instance, if quarks or electrons were composite, high-energy collisions with enormous statistics might produce subtle deviations from point-like behavior. The high-luminosity LHC, HL-LHC, planned to begin operation in the mid-2020s, aims to increase integrated luminosity by a factor of 10. This increase will enhance sensitivity to new physics at the smallest accessible scales and allow more stringent tests of the standard model. Future colliders are also being designed with the goal of pushing the frontier of small distances even further. Concepts such as the Future Circular Collider, FCC, and the proposed Circular Electron-Positron Collider, CEPC, aim to achieve energies well beyond the LHC. By increasing collision energies to hundreds of TeV in the center of mass frame, these machines would improve the resolution scale, potentially probing distances an order of magnitude smaller than the current 1019 meters. At these scales, if quarks or electrons were composite, or if new particles existed at extremely high mass scales, deviations from point-like behavior might finally be observed. The experiments are not just searching for substructure in known particles. They also probe exotic possibilities, including mini black holes, extra dimensions, or the existence of new heavy particles. The reasoning is that at extremely high energies, the collisions might create phenomena that are invisible at lower energies but manifest as deviations in particle scattering, missing energy signals, or production of unexpected resonances. Such searches require extremely precise calibration, detailed understanding of detector response, and sophisticated computational modeling to separate rare signals from overwhelming background events. One of the key experimental techniques in probing small distances is to study scattering at high momentum transfer. In this approach, two particles collide and exchange a large amount of momentum. The higher the momentum transfer, the smaller the distance being probed. In collider physics, momentum transfer is often measured in GeV or TeV, and the relationship between energy and spatial resolution is direct. For quarks and electrons, no deviations from expected scattering patterns have been observed at momentum transfers, corresponding to distances of 1019 meters. These experiments effectively set upper limits on any potential size or compositeness of these particles. The absence of observed substructure in quarks and electrons has profound implications for theoretical physics. It means that, at least down to the smallest distances accessible with current technology, these particles are fundamental in the sense described by the standard model. This experimental result constrains models of new physics, ruling out any compositeness scale smaller than the current resolution. It also means that the standard model remains remarkably robust, with quarks and electrons behaving exactly as point-like entities across a range of energies and distances. Collider experiments also provide indirect insights into the fundamental length scales of nature. While we cannot directly measure the Planck length or probe spacetime at 1035 meters, pushing measurements down to 1019 meters provides critical benchmarks. Any deviation observed at these scales would signal new physics and potentially guide theoretical development toward understanding the ultimate limits of spacetime structure. So far, the absence of deviations reinforces the notion that the smallest measurable structures are still point-like particles, and any new physics, if it exists, lies at scales beyond current experimental reach. The continuous upgrades to collider technology reflect the scientific drive to probe smaller scales. The HL-LHC will provide unprecedented data volume, allowing statistical analysis of rare events. More powerful magnets, improved detectors, and faster electronics enhance the precision of measurements, increasing the effective resolution in probing fundamental particles. Even as we push these technologies to their limits, the fundamental question remains: are quarks and electrons truly point-like, or is there an unseen layer waiting to be revealed at even smaller distances? Computational advances complement experimental efforts. Simulations of high-energy collisions allow physicists to model billions of potential interactions, predict expected scattering distributions, and identify anomalies that might suggest new structures. Machine learning and advanced data analysis techniques are increasingly used to sift through enormous datasets, maximizing the sensitivity to rare phenomena. These computational tools are essential for interpreting the results of collisions at the highest energies and for planning future experiments designed to probe even smaller scales. Future colliders such as the FCC and CEPC aim not only to increase collision energies, but also to improve luminosity and precision. Electron-positron colliders offer cleaner experimental environments than proton colliders, reducing background noise and allowing more precise measurements of particle interactions. By combining higher energies with high precision, these machines could push the experimental frontier of measurable distances closer to the Planck scale, although direct observation of Planck scale phenomena remains far beyond current capabilities. The results of collider physics also tie into broader questions about the nature of matter. Understanding whether quarks and electrons are truly point-like informs our understanding of the forces that govern their interactions. If substructure were discovered, it would reshape particle physics, leading to a revision of the standard model and potentially unifying it with other frameworks, including quantum gravity. The absence of substructure, however, reinforces the notion that the standard model's description of elementary particles remains valid across an astonishingly wide range of energies and distances. In practice, the LHC and future colliders represent a remarkable achievement in human technology and ingenuity. Accelerating particles to near-light speed, controlling their trajectories with superconducting magnets, detecting billions of collision events per second, and analyzing these events with precision requires decades of engineering, coordination, and theoretical insight. The ability to probe distances as small as 1019 meters is a testament to the power of combining experimental skill with theoretical understanding. Beyond searching for substructure, these experiments also test the fundamental symmetries of nature. Collisions at the smallest scales probe charge parity violations, rare decays, and other subtle effects predicted by the standard model. Each measurement at these extreme resolutions provides constraints on possible extensions of the theory, including supersymmetry, extra dimensions, and composite models of fundamental particles. The consistency of results across a vast range of energies underscores the robustness of current physical laws, while highlighting the extraordinary precision achievable in modern collider physics. High luminosity, high energy, and advanced detector technologies collectively define the smallest measurable distances achievable today. Colliders like the LHC are pushing physics to 1019 meters, revealing no substructure in quarks or electrons. Could there be something smaller? Modern physics has mapped the universe down to astonishingly small scales. Quarks and electrons probed at distances as tiny as 1019 meters appear to be truly fundamental. The Large Hadron Collider and decades of high-energy experiments have confirmed that, at the smallest accessible scales, these particles behave as point-like entities, showing no measurable internal structure. Yet, theoretical physics continues to ask a deeper question. Are quarks and electrons truly the most elementary constituents of matter? Or could there be an even deeper layer of reality, particles, dimensions, or structures so small that our current experiments cannot detect them? This question drives some of the most speculative but scientifically grounded research in particle physics. One set of hypotheses involves preon models. Preons are hypothetical particles proposed to be constituents of quarks and leptons. The idea emerged in the 1970s and 1980s as physicists explored the possibility that the apparent point-like nature of quarks and electrons could be an emergent property of a deeper composite structure. In preon models, a single quark, such as the up quark, might be made of 2 or 3 preons bound together by forces far stronger than the known strong nuclear force. Electrons, likewise, could be composed of multiple preons. These models attempt to explain the existence of 3 generations of matter, the quantization of electric charge, and the symmetry patterns observed in the Standard Model, by assuming that all quarks and leptons are built from a smaller set of fundamental building blocks. Preon theories, however, face significant theoretical and experimental challenges. The binding energy required to hold preons together must be extraordinarily large, far beyond the energies currently accessible at colliders like the LHC. If preons exist, their composite nature could manifest at extremely high energies as deviations from point-like scattering patterns. Physicists have looked for such deviations in high-energy collisions, searching for substructure in quarks or leptons, but so far none have been observed. These null results place stringent limits on the possible size of preons, suggesting that if they exist, their scale must be smaller than 10 to 19 meters, well beyond current experimental reach. Another speculative avenue for deeper structure involves extraspatial dimensions. In standard physics, we experience 3 spatial dimensions and 1 temporal dimension. However, string theory, as well as certain models of quantum gravity, suggest that additional dimensions could exist but be compactified, curled up into extremely small scales. The sizes of these extra dimensions could range from fractions of a millimeter down to the Planck length, 1035 meters. If these dimensions exist, particles may have properties that arise from their interactions in higher dimensional space. For example, the masses of quarks and leptons, the strengths of the forces, or the apparent structure of particles could be influenced by the geometry of these hidden dimensions. Extra dimensions could also provide an explanation for the relative weakness of gravity compared to the other forces. If gravity can propagate into additional dimensions while other forces remain confined to our familiar 3 dimensions, its apparent strength in our universe would be diluted. Collider experiments, precision measurements of gravity at short distances, and astrophysical observations have all been used to search for evidence of extra dimensions. So far, no conclusive signal has been detected, but these investigations continue to improve sensitivity, probing smaller scales and tighter constraints with every experimental upgrade. The third possibility for a deeper structure comes from quantum foam, a concept arising from quantum gravity. At scales near the Planck length, spacetime itself may fluctuate wildly due to quantum uncertainty. In this picture, space is not smooth but frothy, with geometry fluctuating randomly on extremely small scales. These fluctuations could manifest as tiny distortions in distances, random fluctuations in energy, or even the temporary formation of microscopic wormholes. The term quantum foam was coined by John Wheeler in the 1950s to describe this idea. That at the smallest conceivable scales, space-time is turbulent and indeterminate, rather than continuous and static. Quantum foam implies a fundamental limit to measurement. No experiment could precisely define distances smaller than the Planck length, because spacetime itself would be fluctuating at that scale. This is not a limitation of technology, but a limit imposed by the laws of physics. Any attempt to probe beyond this scale would involve energies so extreme that the very fabric of spacetime would be disrupted, potentially creating black holes or other phenomena that prevent meaningful measurement. The Planck length, 1.616 x 1035 meters, thus represents a natural boundary for the smallest measurable distances, and quantum foam provides a physically grounded explanation for why probing smaller scales may be impossible. None of these possibilities, preons, extra dimensions, or quantum foam, has yet been confirmed experimentally. Preon models predict effects at energy scales beyond current colliders. Extra dimensions may exist at distances far too small to detect, or their influence may be subtle, requiring indirect measurements. Quantum foam operates at the Planck scale, completely inaccessible to current or foreseeable experiments. Despite this, these ideas remain scientifically compelling because they provide frameworks to extend our understanding of the universe beyond the standard model. They are grounded in existing physical principles such as quantum mechanics, relativity, and symmetry, and they generate predictions that can, in principle, be tested with future technologies. Collider physics continues to provide indirect tests of these hypotheses. By studying particle scattering at the highest energies and measuring rare decays with extraordinary precision, physicists can constrain the scale of possible new structures. For instance, deviations in angular distributions, unusual resonances, or violations of expected symmetry patterns could indicate the existence of preons or the influence of extra dimensions. Similarly, observations of high-energy cosmic rays, gamma-ray bursts, or gravitational waves may provide indirect insights into the microscopic structure of spacetime. These studies have not yet yielded evidence, but they guide theoretical work and motivate the design of future experiments. High-luminosity colliders will play a key role in pushing the frontier of the smallest scales. The high-luminosity Large Hadron Collider, scheduled to operate in the 2020s and 2030s, will deliver 10 times the collision statistics of the original LHC. This increase in data will allow searches for extremely rare events that could hint at substructure in fundamental particles. Future proposed colliders, such as the Future Circular Collider or a high-energy linear collider, aim to achieve even higher energies, increasing resolution and sensitivity to hypothetical preons, Kaluza-Klein excitations from extra dimensions, or other exotic phenomena. These machines represent humanity's best chance of testing whether quarks and electrons are truly fundamental, or whether an even deeper layer exists. The possibility of extra dimensions also has implications for the structure of space itself. In some models, the extra dimensions could be warped or curved in such a way that their effects only appear at high energies. Particles might have excitations or modes associated with motion in these hidden dimensions, which could appear as heavy copies of known particles. These Kaluza-Klein modes would provide indirect evidence for the existence of extra dimensions. Searches for these modes are ongoing, with increasingly stringent limits as collider energies and luminosities improve. Quantum foam suggests that at the Planck scale, the concept of distance itself may lose classical meaning. Instead of a smooth metric, space might be probabilistic, with fluctuating distances and undefined geometry. This radical idea challenges our intuition, but it is a natural consequence of combining quantum mechanics with general relativity. While we cannot probe the Planck scale directly, indirect consequences might appear in phenomena such as black hole evaporation, high-energy particle interactions, or the behavior of gravitational waves. These effects are subtle and difficult to detect, but they remain a focus of theoretical research. Preon models, extra dimensions, and quantum foam all share one feature. They propose structures smaller than current experiments can resolve. Preons would lie below 1019 meters, extra dimensions might be as small as 1035 meters, and quantum foam operates precisely at the Planck length. While these scales are vastly different, they illustrate the conceptual hierarchy of possibilities for deeper layers of reality. Even if quarks and electrons appear point-like, the universe may have structure at a level far beyond our current observational horizon. Exploring these possibilities requires both theoretical innovation and technological advancement. Colliders must achieve higher energies, luminosities must increase, and detectors must become more precise. Experiments must be complemented by astrophysical observations and high-precision measurements of fundamental constants. Theoretical models must make predictions that are falsifiable, guiding experimental design. Although no direct evidence has been found, the interplay between theory and experiment continues to refine our understanding of what might exist beyond the standard model. The search for smaller structures also raises fundamental questions about the limits of measurement. If spacetime itself is quantized at the Planck scale, or if prions are bound by extraordinarily strong forces, there may be a physical limit to how deeply we can probe the universe. This limit is not technological, but intrinsic. It is the scale at which the laws of physics themselves prevent further resolution. Yet even without direct access to these scales, physicists can test the implications, constrain models, and search for indirect evidence that points to the existence of a deeper layer of reality. In addition to colliders, other experimental approaches are being considered. High-precision measurements of atomic systems, interferometry experiments, and observations of cosmological phenomena could reveal tiny deviations caused by substructure or extra dimensions. Gravitational wave detectors might probe quantum fluctuations of spacetime, while astrophysical observations could test the behavior of matter and light under extreme conditions. Each of these approaches complements collider physics, expanding the range of scales over which we can search for something smaller. What we can say with certainty. Modern physics has brought us incredibly close to understanding the ultimate building blocks of matter. For centuries, humans believed that atoms were the smallest units of reality, indivisible and fundamental. Experiments in the late 19th and early 20th centuries shattered that notion. The discovery of the electron by J.J. Thomson, followed by Rutherford's gold foil experiment, revealed that atoms are mostly empty space with a dense nucleus at their center. Soon after, the nucleus itself was found to contain protons and neutrons, which were initially thought to be elementary. Further experiments over the last century showed that even protons and neutrons are not fundamental. High-energy scattering experiments revealed that they are made of quarks, bound together by gluons. Deep inelastic scattering, performed first at ESSELAC in the 1960s, provided clear evidence for these point-like constituents. Over the decades, particle accelerators and colliders, culminating in the Large Hadron Collider at CERN, have probed these quarks to increasingly smaller distances. To this day, quarks and leptons, the electron, the muon, the tau, and their neutrino counterparts, show no measurable size or substructure in experiments. They are currently the smallest confirmed constituents of matter, and they behave as if they are point-like, down to distances of roughly 10-19 meters. It is important to distinguish between the smallest experimentally probed scale and the smallest theoretically meaningful scale. The 10-19 meter scale is a limit set by the highest energy collisions achievable in modern colliders. At these scales, electrons and quarks behave precisely as predicted by the standard model, with no evidence of internal structure. This is the smallest scale that human technology has directly accessed. It is a firm experimental fact, supported by decades of high-precision measurements. In contrast, the Planck length, approximately 1.616 x 10 to 35 meters, represents a theoretical boundary far beyond experimental reach. Derived from fundamental constants, the speed of light, the gravitational constant, and the reduced Planck constant, it sets a scale at which quantum gravitational effects are expected to dominate. Below this length, spacetime itself may lose its classical meaning, potentially becoming discrete or foamy. While the Planck length is mathematically and physically significant, no experiment has ever probed it. The distinction is crucial. The smallest measured structures are quarks and leptons, whereas the Planck length represents the smallest theoretically meaningful unit of length in physics. The current frontier of particle physics continues to push these boundaries. At CERN, the Large Hadron Collider is running experiments at collision energies up to 14 tera-electron volts, probing distances near 1019 meters. The high luminosity upgrades will allow even more collisions, increasing the chances of detecting rare phenomena that could hint at substructure or physics beyond the standard model. Around the world, other particle accelerators, including electron-positron colliders, continue to refine our understanding of fundamental interactions and search for new physics. Meanwhile, theoretical physics explores what lies beyond these limits. Quantum gravity research investigates the structure of spacetime at the Planck scale, attempting to reconcile general relativity with quantum mechanics. Loop quantum gravity suggests that space itself may be quantized, made up of discrete loops, while string theory proposes that the fundamental constituents are one-dimensional strings vibrating at scales near the Planck length. Cosmology connects these ideas to the evolution of the universe, from the Big Bang to the formation of cosmic structures, providing potential observational windows into physics at extremely small scales. Despite these efforts, the experimental reality remains clear. Decades of high-energy experiments confirm that quarks and leptons are elementary, point-like particles. No smaller substructure has been observed, and all current measurements are consistent with the standard model. The Planck length, while theoretically fundamental, remains far beyond the reach of any current or near-future experiment. The smallest confirmed entities in our universe are the elementary particles, quarks and leptons behaving as point-like objects down to at least 1019 meters. The smallest meaningful length in physics is the Planck length, 1035 meters, a scale at which our classical notions of space and time may break down. Whether there is anything smaller than this, whether the universe hides a deeper layer of reality, remains unknown. For now, this is the edge of human knowledge, a frontier defined by the precision of our experiments, the reach of our accelerators, and the clarity of the theories that describe the smallest building blocks of nature.